So I think we can start, and the idea today is that let us try to complete system reliability in about 35 minutes and then spend 5 minutes to recap whatever we have done in this course and another 5 minutes to tell you about what lies ahead. And if we are successful, if I am successful in that, then today is the last lecture. So that is the idea. Okay. Okay. So last lecture we were talking about system reliability, but we kind of laid the foundation of talking about system reliability, right? And we said that there are two methods for doing system reliability in general, which are popular. One is based on fault tree, the other is based on whether it will survive or not. So it is known as FMA. The fault tree method is known as failure mode analysis, FMA. The other one is SCA, survival C I forgot, and then A is analysis. So these are more or less the two methods that are prominently used for system reliability analysis. Okay. So what we will do today is that, so by the way, I already told you about this, both of this. So in failure mode analysis or FMA or fault tree, what do? We look at different paths in which failure can happen and compute probability of failure following that path. And then out of those, whatever is maximum, it's independent, right? So you can take that in that sense. You can combine those to find out this probability of failure of the system, right? And it is good if the failure is ductile. I think if the failure is ductile, I think it is good failure mode or brittle. I'll confirm. Okay. In SC is opposite. In SC you look at different modes or different stable configuration approach. SCA. Okay. So you look at different stable configurations in which the system will survive, and then using that you will find out the survival probability. 1 minus survival probability is equal to failure probability of the system. So this is broadly the idea. Okay. And we talked about it a little bit. So let us talk about it a little bit more with one example, let's say. Okay. And let us take one example of truss. So let's take a truss. And even though this is probably a very simple truss, this will, you will realize through this example that how difficult it or how complex it can be even for such a simple system. Okay. So let us see. Okay. Let us number it, maybe 1, 2, 3, 4, 5, 6. So there are 6 members, right? And then although there are additional pin joints wherever the trusses intersect, but we are going to take only the supports as joint. The other things we are going to ignore. We say we should not ignore it, but we are going to ignore, right? So this, and this, and let us call it A, B, C, D. Okay, right? So all of you should be able to tell, and you should tell now, what is the degree of indeterminacy of this truss? 2, 1. So someone is saying 1 and 2 both. So what is the degree of indeterminacy? He is saying 1. Everyone agrees? Do you remember degree of external indeterminacy and degree of internal indeterminacy? There are 2 things. 2. Okay. Why 2? That's not. How do you find degree of indeterminacy of a truss? Each member can take, fixed nahi hai. There is no meaning in having a fixed support in truss because the truss do not carry moment. So how do you find it out? Remember, m plus r minus 2j. Each member has one force, right? So number of member is equal to number of forces because they only take axial load truss. R is the number of reaction. So m plus r is the total number of unknown, right? So what is the total number of unknown? 10. There are 6 members, 12. So 6, 7, 8, 9, 10. So m is 6, r is 4, right? M plus r minus 2j is what you will calculate. Because why 2j? Because at each of the joints you will get two equations, summation fx equal to 0, summation fy equal to 0. So m plus r is equal to 10. How many joints? 4 joints. 2, I mean top 2 are also joints. There also you will apply the equation. So minus 2j. So how many, what is the degree of indeterminacy? 2. So the number 2 was correct, but how he arrived probably was not correct. But I will come to that. Wait. But now the next question is, what is the degree of external indeterminacy and what is the degree of internal indeterminacy? How do you find out external indeterminacy? Number of reaction force minus number of equations. So what is the number of reaction force? 4. Number of equations at joints that will satisfy 3. Because at the joint you will satisfy summation fx0, summation fy0, summation m0. At the support, joint means support, right? So external indeterminacy is 1. So internal is also 1. So that's how 1 plus 1 becomes 2. So the number of indeterminacy, the indeterminacy is 2, out of which 1 is external, one is internal. What does it mean? It means that if 2 of the conditions in the, let's say C and D fails. C and D are the load carrying capacity of the joint. Let's say the load support is not able to carry C and D. So that means it will fail because the external indeterminacy has now gone to negative. Although the member itself is stable, but because the external has gone to negative, it will fail because of external motion. And you can understand, if C and D fails, that means that joint is not there, so it will keep rotating. The whole thing will keep rotating, right? So that is what it means, because it is going to negative. Similarly, internal indeterminacy is equal to 1 also. So that means if 2 members fail, this will also fail. And you can imagine if, let's say 5 and, okay, I have not given load, let me also give load, right? Let's say the load is like this. So now as we assume 5 and 6 has failed. Because of that loading, the top member will go away and it will not be able to carry those loads basically. Okay, it will not be able to carry those loads. So if 5 and 6 fails, basically again this will fail. Okay. So the degree of indeterminacy decides what is the redundancy of the system. And in this system, this is a specific system I have taken, the external one is 1, the internal one is 1, total is 2. So that means I can afford to, for example, let's say support, the second support C, it fails in C, it does not carry loads in C. And along with that member 6 fails, then it is still stable. So the system will be stable as long as internal is going to 0 and external is going to 0. But if either internal or external becomes negative, then the system will fail. Okay. So what are the failure paths? I will not write all of those, I cannot write all of those, but let us see. So if I have to write down the failure path, one option is A and B failing. If A and B fails, the system fails. So and you can write all the combinations of this joint, so A, B, B, C, B, D and all of these things. B, C, So if any of this happens, it will fail, and this concerns the two supports. So this will ensure that it fails because of external, external indeterminacy going to negative. Now if I look into the members, only members, then how it can fail? Any two member failing, it will fail. You can write, let's write with 5, 6, 5, 1, 5, 2, 5, 4, and then you can write 6, 1, 6, 2, 6, 4. Then you can write 5, 4, 1, 4, 2, 4, 3, 4, 4 does not make a sense, 4, 5 and 4, 6 are already taken. If 5, 2 fails, it does not survive. No, because of this bottom one, right? So what will happen is that if 5 fails and 2 fails, then you are having something like this, right? So what will happen is that because of this loading configuration, some reaction force will come in here, and because of that, there is nothing to balance that at this joint. At this joint, you will not be able to solve it. So when you solve for it, because you will equate the moment and forces, you will see that some force will come here, and because of that force, there is nothing to balance it out. So it will not be an equilibrium. Basically, that's the point. Okay. Yes, you are right. This portion is actually fine. This sub portion is fine, and that will happen in many other cases. But as a whole, and that's why I draw that diagram, right? It means that the truss should be able to carry all 3 loads. That's what failure is. You can imagine what is failure. I mean, that also is a philosophical discussion. So you can say that the truss is safe if it have the capability to carry all these 3 loads. So will it be able to carry all those? So that's what you need to see. Okay. And like that, you can come up with other configurations. I'm not writing those. And then there will be a third scenario where it will be a combination of joint support failure and member failure. And in that case, it will be 3 elements coming into picture, because you can afford, let's say, 5 failing, 3 failing, and then you need either one more support to fail or one more member to fail. So 5C, let's say B. So then it will start failing, and like that you can write. I'm not even checking, but you can think that there will be 3 things coming together in that case. Okay. So this is what will happen in this case. That is what will happen in this case. So you can imagine that even for such a small thing, the number of failure paths is quite large. And then once you have done that, what you will do? You will write the safe event and then form a tree where each of this is possible failure modes, right? Each of this is possible failure mode. Some of this can even be broken further. For example, first C is failing, and then 5CB. So there you know that if C and B fails, anyways the system fails. But if 5 fails and then CB fails, then also it is failed. So in that case, that becomes a subset. And like that, you can form a tree kind of structure, which is known as the fault tree. And then from this, you will look at the most probable path of failure, and that failure path will give you the failure probability. And these paths are generally, independent, the way you write it. And these are known as cut sets. These are known as cut sets, because you are cutting this structure and looking at how it can fail. So that is the name. Yeah. Yes, obviously, it's a headache. So no doubt about that. And you can understand, that's why I took this example. This was the smallest possible example you can imagine, and you can look at what is happening there, right? Imagine a large thing, and that is why the opposite one is the SCA is more preferred, where you look at the way it can survive. The way it can survive is actually much easier to find, and because of this large number, you can imagine that it is very common that you might miss one or two failure modes. You have to note it down. One or two you might miss, right? It's possible. In that case, this will start underestimating. It will give a smaller failure probability. Why? Because these are union, right? This is series failure. So it will be first cut set probability plus second cut set probability plus third plus fourth. If you miss something, that means the failure probability is getting reduced, which means you are in trouble. Where you are designing assuming that it is 10 to the minus 5, whereas in reality it is 10 to the minus 3. And with so many failure modes, it's very natural that it can happen. So that is why the other one is stable configuration is referred, because there you will look at the way it can be in stable configurations. This member fell, it's still stable, and you will write those down. In some cases that number might be less, in some cases that number might be more than this. But there if you miss something, you are overestimating. So that is why this is used mostly when there is ductile failure. If I am correct, I forgot, but I think for ductile failure, because ductile failure, if you miss something, there is you will get a warning, right? And it's safe. For brittle failure, if you miss something, it will be catastrophic failure, and that will be thing. So based on that logic, I am saying, and I think I am correct. Okay. Yeah. Yes. So there you can, in the sense that for building, you will first create these cuts in each floor failing, and then within each floor slab, beam, and all of those things. So you have to do it in system of systems. So you have to take the smallest possible system, devise for it, and then the higher level system will be on based of the smallest level system. Yes, obviously. So that will happen. So that's why you generally these cut sets are generally independent, right? So you will decide those subsystems in a way that they are probably independent. Otherwise, you will not be able to do it. But you are correct, and that is what we will discuss next. Okay. So you can understand the complexity of this fault-free approach, right? Even for a small problem, such as a simple truss, academic problem, not even academic, a class problem. I mean, first year course we do that problem, right? We find out what is the degree of indeterminacy for that problem. That's a very standard question we ask. And the question that I asked at the beginning is a very standard question we ask in APL 100 or AML 1000, so which is a first year undergrad engineering mechanics course. But truss is introduced for the first time, right? Okay. So this is what we will do. I mean, here, this is not safe actually, right? This is PF also. I mean, basically system reliability, whatever. Okay. But an important point as was raised was that in most cases we will not know how the modes are interacting, they are correlated, independent or not, and that is why we will not be able to find out what is the exact system reliability. Rather we work with bounds, right? And let us see how we can work with bounds. We will take two scenarios, first order and second order, series system and parallel system. For each system there is first order, second order, third order kind of bounds. We will only do first order bound. Okay. So let us see. Obviously the higher the order you go, the narrower the bound will become. I mean, that is obvious, right? But we will do first order. So bounds in, so I have 15 minutes, right? In system reliability. Let us start with the series system or the weakest link system, okay? Series system. Okay. And just to be on the safer side, we will take, not to be on the safer side, just to make our life easier, we will take 3 failure modes, E1, E2, E3. Okay. Series system. We assume E1, E2, E3 as 3 failure modes. So what is the probability of failure? What is the failure probability? Union, not plus. Plus only happens when they are here. Okay. E1, union E2, union E3. This is equal to plus probability of E3 minus probability, then right, all of you know about this, right? Nothing new. Correct. So in this case, first order bound means I will only retain the first order terms, which is E1, E2, E3, right? And that's why it is called first order bound. If I only retain E1, E2, E3, the other terms I am going to ignore. So the other term combiningly will give me a positive number or a negative number. The second order and third order terms combiningly will give me a positive or negative. Negative. Why? I mean, obviously, E1 and E2 occurring together will always be more than E1, E2, E3 occurring together. At the best case, they can be equal, right? So it will always be negative, right? 0 or negative, to be very honest. 0 when E1, E2, E3 are, yeah, do not have any intersection. So in that case, that will become 0 otherwise, right? So as you correctly said, right? All of you correctly said, or most of you correctly said, what happened? I changed the color? No? Yeah. This portion is less than equal to 0, right? So then can I not write probability of f, which is probability of E1 in this f should not be written, right? This should be more of like this. E1, this is less than equal to probability of E1 plus probability of E2 plus probability of E3, right? Because the negative portion was going to reduce that term. So if the reduction is because of this less than equal to sign, I can remove that and I can write that, right? E3, yeah, obviously. Yes. Okay. So in a generic sense, I can write probability of union EI is less than equal to summation over P of EI, right? So I got one of the bound, which is the upper bound, right? What about the lower bound? Then I have to write 0 to 1. That is the bound we know, right? Obviously not 0. We cannot. I mean, that bound is not meaningful. Some meaning. Yeah. So what is that? No. E1, E2, E3. What do you think is the bound on that? No. That is the case when E1 is equal to E2 equal to E3. Least or maximum? You were thinking in a correct direction, but maximum. Maximum of E1, E2, E3. That is the thing, right? The base thing is other two becoming 0. That will never happen. Or other thing becoming an exact subset of, if E2 is a subset of E1 and E3 is a subset of E2, then you will end up with E1, right? So the other limit is maximum of EI. So therefore from here, the other one obviously you should be able to justify in one sentence. I am not writing that one sentence, but if it comes in exam, you have to justify that with one sentence. why it is maximum of that, the one that we discussed, but I am not writing. So maximum of probability of EI less than equal to, let's say PF less than equal to summation over I. Now there is one mistake I have done. Can you tell me? Is this bound correct or there is a mistake? What happens is that right hand summation, can it not go above 1? So then I should put a bound that it is minimum of whatever it is, right? So this is fine, but actually this should be this and minimum of whatever it is. Wait. One second. Summation of this and then minimum of.
Anyway, if you minus that term which is less than 0, all the combinations, automatically maybe chances are that it will go less than 1.
No.
While we are removing.
You have already removed it.
Yeah,
that's the first order approximation, right?
If you don't remove, then automatically.
If you don't remove, who will give you those E1 interest in E2 that you don't know? You only told me, right, that the correlation will not be known. If the correlation is known, why should I do this? Why should I care about bounds? I will say the exact probability. All of this is coming because I do not know the correlation. And when I say first order, I mean I don't know any correlation. If I have to go to second order, then I have to know some correlation. If I know the correlation, then why should I care about bound, right? I should find out the exact thing. I cannot find the exact thing because I do not know the correlation. That is the whole idea, or at least don't know it precisely. So the bound is between this, right? And this is not a very good bound, but this is better than 0 to 1, because anything under the sky is 0 to 1, we know. So this is better than that, but it's not a very good bound. So if you go to second order, that will be a little bit better. Okay. So in the slide, the second order bound is given. You should do the derivation on your own, but the bound at least is there on at the end of the slide. Okay. Okay. So this is for series. Now let us do for parallel. Parallel system. In parallel system, the same problem. I want to find out probability of E1, E2, E3. This is what I want to find out, right? So how will I find it out? This is intersection. How will I find it out? Let us do one thing. Let us reduce it even further. That will help you visualize it. So let us, instead of taking 3, let us take 2. And now you tell me, how will I find it out? No, for one thing he already mentioned. We should take the minimum of, so one bound is minimum of E1 and E2. Because it is intersection. So whatever is minimum of that, if I assume that, that will become one bound. So one of the bound will be minimum of E1 and E2, and it will always be less than equal to that. So it will always be less than minimum of probability of EI. And the idea is very simple. This thing, right? This will always be less than that. But when can you this and this be closest? When this is like this. And then it will be that less than equal to will become equal to. It will be a subset. Apart from that, whatever you take, it will always be less than whatever you take, right? Just by looking at this, you can understand. Okay. So it is obviously, no matter if it even slightly goes outside, whatever is the minimum of that, you can understand that this intersection is always less than that, right? You can always write maximum, but then that is a bad bound. because out of the maximum and minimum, you know that it is going to be min. Like let us take a max. So even in this case, you know that this is less than this whole thing. So that's why you should take the minimum. Maximum will become a very bad bound, and the optimum one will be when it will be equal to is when, I mean, it can be anywhere in between, but I am showing inside, right? In that case, it will be minimum will be equal to that intersection, right? Clear? What? Okay. Let's use 3 colors. Will you agree if I say this red portion is always less than this violet portion? You agree? When the red portion will be equal to the violet portion? So this part you agree. Now the same thing I can say for this portion also, right? The red portion is always less than equal to this bigger or one also, right? And when it will be equal, it will never be equal in this case, because even if it goes inside, then also the other one will take over. So that means let's take it. Let's say this is 0.5, this is 0.05. Now this value is x. So x I am saying is less than equal to 0.05, which automatically means x less than equal to 0.5. But why will I write 0.5 when I know it is less than equal to 0.05? It does not mean the other one will not hold. If 5 is less than 8, then obviously something less than 5 is also less than 8, or something greater than 8 is also will also hold that property. But the idea is that which one is a better bound, right? Clear? So this was the easier one. What is the other bound? What is the other bound? Let us see. Probability of E1 complement intersection E2 complement is equal to 1 minus probability of E1 union E2 whole complement. No, not plus. No, sorry, not one. This is okay. This one. You are aware of this formula? Right? Which is equal to what I was writing, 1 minus probability of E1. This formula again you can draw from set theory. This is E1, this is E2. I am saying what is the area where E1 has not occurred and E2 has not occurred. What is that area? This whole area, right? This whole area. You agree, right? Which is equal to E1 and E2 occurring and then the complement of that. That is what I have written. Which is equal to 1 minus E1. So there is a name for it, and someone first proposed this law, but I forgot the name. But yeah, this is a very well known thing. And you can also do the other way also. Okay. That E1 complement union E2 complement is equal to that thing. De Morgan, right? De Morgan's law. Okay. So this one is fine. So then we want to find probability of E1 intersection E2. In our case, this is what we want to find out. Correct? This is equal to probability of the opposite of that. So E1 not occurring, union E2 not occurring, and the complement of that. Right? Which is equal to 1 minus probability of E1 not occurring, union E2 not occurring. Right? This is fine. Now this one you can extend and write E1, E2, E3 and all of those things you can write, right? Now what is the bound of this? We just now discussed in series system. What is the bound for this? This is less than equal to probability of E1 complement plus probability of E2 complement, right? This we did where? We did here, the top one, right? Which is less than equal to, if I have to generalize it, so summation of 1 minus probability of EI sum over I. This is only for this portion, by the way. Remember, this is only for this portion. This 1 minus is sitting. So then combine it, what will you get? This is a negative sign. So you will end up with oh, by the way, this is only for now, the negative sign comes into picture. So negative less than equal to will become greater than equal to. So what you will end up with is probability of intersection of EI, right, is equal to or greater than equal to 1 minus, and because of this minus sign, the less than is becoming greater than, summation over I 1 minus P of EI. Okay. Probably not, because yeah, I mean, if it gives, then you will take the 0 also. 0 bound will obviously it can come. The same logic is 0 can come. It depends on the value of Pi, but it can give, right, by the same logic. Because if PEI, that summation is, PEI is very small, then summation of that will become very large. And because it will become very large, 1 minus large will give a negative value. So in that case, it should take 0. So it should be obviously minimum of maximum of 0 and whatever it is, because it will give negative, so maximum. In our case, yes, but I mean, depends. In our case, yes, but this is a bound that is not used, right? So in this case, you will end up with maximum of 0, 1 minus summation I, 1 minus P of EI less than equal to P of F less than equal to minimum of P of EI, right? So this is the first order bound for parallel system. Very good. I have finished by, I'm 5 minutes late, but I finished system reliability. Okay. So this is how you can find out the bounds. For second order bound, you should also consider some additional term. The bound will become tighter. The expression will become complex. It's a trade-off. Okay. So that brings us to the end of system reliability. Obviously not the end of system reliability, to the end of what I wanted to cover in system reliability, right? And just to, what are the things that we are not covering? One of the things that is very integral to reliability is time dependent reliability, because when you design something, you design it to perform reliably over its lifetime, which means the reliability changes and then with time. So you should compute time dependent reliability, but that is something that we are skipping, or mostly because many of you might not have background in vibration, at least the UGs did not have, so that is one reason. The other thing is that some of you are also doing some project on that, so that part is there, right, in that sense, but it's not in the syllabus, time dependent reliability. Another thing that I'm ignoring is something known as sensitivity. There are 10 or hundreds of random variables, and because of that my output is random. But are all those 100 random variables equally important? Now in a usual setting, you will take the gradient and you will say that I will use the gradient to measure whether it is important or not. Gradient is sensitivity. But in a probabilistic sense, you cannot do that because those are random. So gradient at which point? So sensitivity analysis is a useful topic where there are primarily two types of sensitivity that we compute. One is based on Sobol indices or Sobol, which assumes that the output is Gaussian, symmetric, and that is also known as variance based sensitivity. So we only need the variance to compute the sensitivity. The other one is moment independent sensitivity, where you compute the sensitivity based on PDF, the shift in PDF. That is also known as distribution based sensitivity. So one is variance based sensitivity, the other is distribution based sensitivity. So if you are interested, you should study this, again not in the syllabus, but you can study those are important topics. Okay. So these two things I did not cover, everything else we have covered in this course. Okay. If Saturday was a lecture, I would have gone a little bit deeper into the sensitivity part at least. Of so that is a different course. There is a different course on uncertainty quantification and propagation. So that's a different course, which I have taught it once, but I'm not sure next semester it will be. I think right now it is not there, at least in the next semester, but sometime it will be taught again. Okay. In many cases, yes, I at least like to look into this, but then some people will not agree, because the post-processing part is actually significant, at least the system reliability and all of those things. In system reliability, you are not actually quantifying the uncertainty, but you are computing the reliability only. But I personally think, yes, reliability is a subset of uncertainty. Whatever you learn in uncertainty can be used here, and there is inverse uncertainty quantification also coming into picture. Some will say uncertainty quantification is a pre-processing of reliability. How? In reliability, remember we are saying that the input variable is random and you know the distribution. In reality, you will not know the distribution. So how will you get that? By solving an uncertainty quantification problem. So now if I try to look or start to look from that lens, UQ becomes a pre-processing where you first use UQ to find out the uncertainty in your input and then use that to quantify reliability. That is another way of looking into things. But mostly in uncertainty quantification, you are only interested in the PDFs. In reliability, you are interested in the probability of failure. That's the primary distinction I will like you to take home from this course. Okay. And for me, reliability is a subset of uncertainty, but there are different philosophies. Not everyone will agree, and I am fine with that. Not everyone has to agree, right? Everyone should have their own philosophy. Okay. So to conclude this course, what are the things we have covered in this course? We started with some basic review of prob and stat. From there, we went to define what is a limit state function or a performance function. What is the reliability index, Cornell's reliability index. From there, we went to Reques-Fissler algorithm and all of those things, right? After that, we went into first order second moment methods, where we talked about MBFOSM. We told or discussed why that is not useful. We discussed why F4M is better in variance, but we also discussed why F4M is not good for nonlinear systems, for systems having multiple failure points. And from there, at least for the nonlinear part, we went to SOM. SOM is little bit better because at least second order is there, but it's still not perfect for highly nonlinear system, and multiple failure point issue still comes into picture. From there, we said that there is HRM also, we will not discuss that. That is not in the syllabus. So we went to simulation based approach or sampling based approach. In sampling based approach, we started with the law of large number, vanilla Monte Carlo and all of those things. And we realized we need tens of millions or hundreds of millions of samples for a realistic failure probability. Not that useful. So we said, okay, how can we reduce this number of samples? So we said, okay, let us go to importance sampling. Okay, importance sampling will only sample from a distribution and then weigh it. The problem, what sample to distribute for, sample from? We said that, okay, let us do the maths and find out with the optimal distribution to sample from. It ended up that optimal distribution is a function of probability of failure, which we do not know. We said we cannot use it. So what to do? Go back to form, solve the form problem. The MPP problem, the MPP, the most probable point, is a point that is very close to the failure domain. So let us form a distribution with MPP as the mean and draw samples from that, and that becomes our ISD, importance sampling density, and using that let us now do IS. Said okay, that is somewhat better. Is there some alternatives? Yes, there is. Subset simulation. Instead of doing a very small failure probability, let us do it in a product form, and each of those product will be a finite number, 0.1, 0.2. Those are the standard numbers, P naught. And using that, we can now do subset simulation. But for doing subset simulation, you want to sample from conditionals or half known conditionals in many cases. I mean, you know it as the numerator, but the denominator is unknown. So it's an unnormalized distribution. How to sample from the conditional or unnormalized conditional in most cases? Well, there is metropolis testing. You do metropolis testing to compute each of the conditional, do the product along with the first thing, and you find out the probability of failure. But no matter what you do, sampling is very expensive. What can we do? We cannot go back to form, that is not so accurate. So surrogate based approach. In surrogate based approach, the idea is we will do sampling, but let us first build a surrogate model, and we will sample the surrogate model, not the actual simulator. What are the different surrogate models possible? Well, we talked about 3-4 at least. The first one is response surface, which is the polynomial regression. Then we said that okay, polynomial. What polynomial? Let us do orthogonal polynomial. That gives us the polynomial chaos. But we are learning a surrogate. It is coming from data. The data is limited. What about the uncertainty because of limited data? There comes the Gaussian process, which captures the uncertainty because of limited data, and also noisy. I am not telling noisy because here the data is from simulation. There are others also, neural network, we did not talk about that. And that we did all of this, and then we said okay, we can do analysis, but as an engineer our job is to design. So can we design while incorporating this uncertainty or probabilistic constraints? There comes design under uncertainty. In design under uncertainty, we talked about two things. One is minimizing the propagation of uncertainty from the input to output, which is the robust design optimization. The other one is ensuring reliability, which is the reliability based design optimization. I also mentioned you can combine the two, although I did not talk about that after that, but you can. But in either of these, the problem is that you now need to compute gradients with respect to something that is probabilistic, and we showed how you can do that. In RBDO and RDO both you can do that, and we talked about how you can compute those sensitivities. Those are on the technical side of things. You will not need those sensitivities if you are using some gradient free optimizer. You only need those when you are doing some gradient based optimizer. Keep that in mind. Then we said okay, until now we are talking only about component. What about the system? So let us go and now think about system reliability. In system reliability, we spent 2 lectures, last lecture and today's lecture. Last lecture we talked about what is system reliability, why is it so complex, why is it an unsolved problem in most cases. It is an unsolved problem, it's an open problem. Okay, if you are working on reliability in today's time, that's the problem you should do a PhD on. Okay. In system reliability, we talked about 2 extremes: series system, weakest link system, parallel system, redundant system. I mean, parallel and redundant are same, weakest link and series are same. But in reality, it will not be either of those, it will be something hybrid, which we call K out of N system sometimes, or hybrid systems. So for a hybrid system, what will you do? And those are the real systems. Well, you have 2 approaches. One is you go the route of the failure mode analysis, which is based on fault tree. The other one is stable configuration analysis, or the SCA, which is the survival tree. And either of these you can do. One will give underestimate, one will overestimate, one is better for brittle, other is better for ductile, and so on and so forth. This is overall what we have covered in this course. This is your syllabus for the majors. Okay. Some of the things that I would like to mention. So yeah, these are some failure modes, but yeah, the bounds. This is the second order bound, and yeah, right. This is the comma 0 you mentioned, and that is it. Okay. So with that, one more thing. Let me go back to the last week slides. Okay, I mean last lecture slides, and that is the last thing we will do. I mean the previous one. This is yeah. Because one thing that I discussed, I said I will tell you, is the SCA versus FMA is failure mode approach, SCA is stable configuration approach. So the name was correct. And then there is different methods and all of those things there, right? So the names were correct. Okay. So with that, we come to the conclusion of this course. You will receive some emails from me regarding measures, regarding project, and all of those things. I mean, this is conclusion of the lectures of this course. The course has not concluded. There are things that are remaining, but at least the lecture component has concluded, right? Okay. Thank you. So we will have no more. We will not have any lecture. Yeah. Thank you.